In this tutorial video, we're going to review some of the methods for classification using Python. Classification is a type of machine learning where we're going to try to distinguish between data sets. In this example, we're going to try to identify some numbers, and I'll show you 8 different methods for classification. You can follow along with source code. I'll add a link to the video in the comments. So classification is a problem identifying which set of categories are based on observation features. We call these features the inputs to the model, and then the labels are the outputs. Now you can either have problems where the labels, the outputs are known, and that would be something like supervised learning. If you don't know the labels, then it would be unsupervised learning. So if I just gave you all these images right here and I told you they're different numbers, you need to distinguish between different numbers, I don't tell you what they are, then that would be unsupervised learning. But in this case we're going to do supervised learning because there is a label with each of these that tells what is the correct answer. And we can use that for our training and also in validation. So we're going to create a support vector classifier and 7 other methods in Python, and it's almost as easy as this, where you create your classifier with this first line, you fit it with the inputs. Those are your observations, and then these are your labels, these are your outcomes or outputs. And if you have an unsupervised learning, you just don't have these right here, but you still use the fit function just with your observations or inputs. Okay, and then once we've trained it, then we predict. And so we're going to use something that we didn't use to train it to try to predict and compare with the labels that are there to see how accurate it is. Okay, each of these right here are an 8 by 8 image, so 8 pixels by 8 pixels, and we're going to translate those into a sequence of numbers that we're going to use to train this. Alright, and you may have seen, you go to your cell phone and use an app like Google Translate, and you can put it over things and say translate into Korean, for example, or some other language, and it will augment the image. So it's identifying the characters, and then on the back end doing a translation, and you could select different languages. Here's Arabic, for example. So I was able to recognize those characters and then do the translation. So you can do any number of languages and it's just going to translate. And it does an okay job. I like how it even puts the background in there, which is nice. When you get to complex images, it'll still look like it was almost written in that language, or at least a somewhat decent translation a lot of the time. Okay, so let me close this out. Okay, so we have classification. We're going to just open up a Jupyter notebook, and we'll from sklearn import datasets and support vector machines. We'll do this as our first test case, and then we'll do the train test split. And here's our digits dataset. So that comes with sklearn, and these are just a sequence of I think like 1700 or 1800 numbers with the associated labels, and the numbers are these 8 by 8 images. We're just going to reshape it into just a flat vector, create our support vector machine with gamma. That's one of the tuning parameters of this, and then split into 50-50 into test and training. And then we'll learn the digits on the first half with the labels. Okay, and then if I run this, you can see it's going to just create this support vector classifier. It shows you all of the different options here as I fit it. Alright, and then I want to test it on the second half of the data. I'll just create a random number somewhere in that list and show the image and then predict it as well. So let's go ahead and just see what happens here. We have predicted equals 3, 6, 3, 8, and I can run this any number of times until I think it might have gotten one wrong. Okay, so that might be a 4. I'm not sure. It says it's a 9, but you can see that sometimes you're going to maybe even disagree with what it came up with. Okay, but alright, there it is. We have predicted, and then we could also print out what the actual target is, or the actual label on how it was trained. Okay, but let's show let's show some other classifiers as well. In addition to the support vector classifier, I'm going to time each of these, and just like I did before, I'll just load it and then reshape it and split. Okay, now this is logistic regression. Logistic regression, it's a machine learning algorithm for classification. It's very common in neural networks. Often the last layer condenses the influence of several independent variables on a single outcome, and but it assumes all the predictors are independent of each other, and assumes the data is free of any missing values. Okay, so that's a disadvantage of logistic regression. Naive Bayes. This is let me finish the logistic regression here. Okay, and then naive Bayes is the next one. Okay, this one is known to be very fast compared to more sophisticated methods, and so sometimes you get that speed trade-off, and that's desirable. But it's also known to be a worse estimator. So you might give up some of the accuracy for speed. Okay, so let's go on to the next one, stochastic gradient descent. Okay, and that one, it is efficient and easy to use and implement. Requires a number of parameters and is sensitive to feature scaling. So you can see a couple additional parameters there that we had to put in. Alright, let's go on to the next one, k nearest neighbors. It's simple, robust, even to noisy training data. It's effective even if the training data is large, but it needs to determine this k value. Basically, I put in neighbors 10, and it also has a higher computational cost because it needs to basically store all the instances, and then and also to all the training samples. Okay, let's go on to the next one, decision trees. Decision trees are simple to understand and visualize, and require little data preparation. They can handle numerical and categorical data as well. Decision trees, they don't generalize well, and they can be unstable. Small variations can result in a different answer altogether. Okay, let's go to random forest. Random forest. Alright, so this one, the advantage is the reduction in overfitting, and the random forest is more accurate than decision trees in most cases. So it's going to be a little bit better than the decision tree, but it's slow in its real-time prediction. It's difficult to implement, and it's a complex algorithm. Alright, support vector classifier, we've already seen that one. It's effective in high dimension spaces, so when you have a lot of different features, or you also have many different labels that you're trying to predict. And it uses a subset of training points, so it's also memory efficient. Now, it doesn't provide probability estimates. It just gives you an answer one way or the other, and they're calculated, anyway, so that's a support vector classifier. Let's go on to neural network. When we think of deep learning or artificial neural networks, this is a very common one. This is just another type of classifier. It's especially valuable when the space is very nonlinear, and there's no prior knowledge needed to be able to set this up. but they don't extrapolate well outside of the training because they're so nonlinear. If you go outside of the training set, it's going to be a poor prediction generally. All right, and you can also overfit these as well. All right, so these are all the classification methods, the 8, and you can see the, I just put a label, not a label, a string on each of these so I could just do it with a loop, because for each one of them for training in this loop, I'm just going to do this fit of XA and YA, and then I'm going to time it. So I'm going to do a start time and a finish time just so I can print that out with the time. Alright, so let's go ahead and run this one. You can see a warning here, and the packages typically do a good job of warning you convergence, failed to converge, increase the number of iterations. So let's go back up for logistic regression and just add something here. I'm going to, on max iterations, I'm just going to increase that to 5,000. Alright, and then run it again. Alright, and I think I just swapped these. Let's see. Oh, no, I've got them right there. Okay, so that's the order. I just declared this in a slightly different order than I put them in above. You can see logistic regression, I increased the number of iterations for the solver. It increased the time by quite a bit, but then that warning went away that it didn't converge. Okay, it actually still gives me a pretty good solution even if it didn't converge there. But then we're going to now test it. So we did the training, and now we're just going to test it on the second set, and this is going to be our predictions, and we'll just show the image with all of the predictors. Okay, you can see that all of them are very fast. Okay, this one is the one that's just a little bit slower. Okay, the random forest. Okay, so here's 5. You can see that this one, there's a little bit of confusion here, whether that's a 9, a 5, or a 6. And I would be confused as well, which is kind of interesting. The algorithms kind of split. Naive Bayes, Logistic Regression, both said 6. We had some 5s, and we even had a 9 here. So I'd be kind of split on this number too. The label says 5, so you can see which ones got it correct, but this is not data that we trained on. It's the one that we're using for validation. Alright, here's a 9 or a 1. Again, interesting that this 1 it's more like a Italian one or European one here. I've seen some people write their 1s this way. And alright, so there we have another one. Okay, these all agree. This is a 3. That's a pretty clear case of a 3 there. And there's 6, and you can run this over and over again just to see what it's predicting and if they all agree. You could also set this up like in a loop to just test all of them and evaluate the performance. Okay, you can also, in these classifiers, to improve it, you can use packages like HyperOpt or others. You got so many parameters here. Sometimes you're just guessing, running it again, and checking. You can use some of these packages to automatically give you the best parameters on your validation or test set. Okay, so that's it for the number classification. Again, there are additional examples on this website. If you just come to the link, alright, and yeah, it will be here on the right hand side. Just come down to the machine learning area, and you've got classification, deep learning, LSTM, and others. And just select classification here, you'll see the number example with the source code for that, and then also these other test sets which show these 6 cases where you have a homogeneous population and then also segregated clusters. So I'm not going to run each of these, but I wanted to show you the results with these 8 different classifiers. You can generate the data there. There's how you generate it. And then it's going to go down through and just show you how to do each of these. Here's logistic regression, and you can see it's a linear classifier. So it doesn't do the best job here on some of these. You have the incorrects are the orange. So anytime you see orange show up, then it's not doing a very good job of classifying that. Okay, here's the next one, naive Bayes. This one does a fairly good job. This one on the right, it missed at some of this intersection. It's known to be fast. You've got, maybe a lot of data. It's going to be quick to train and also to retrieve, but it's not the best classifier. Okay, stochastic gradient descent. Okay, again, there's some issues with that. Maybe some of the tuning parameters could help these. But here is k nearest neighbors. Now this one's a fairly robust one. It does a fairly good job. It just looks at which one does it belong to in terms of its nearest neighbors. And you can see there's a little bit of yellow right at the intersection of some of these, but overall it does a fairly good job on these 6 test cases. Alright, decision tree is the next one, and this one also does a fairly good job. There's just some between the data sets where it misclassifies them, but that's kind of expected. Okay, random forest. Okay, again, just a few at the intersection between them. Very well. And then here's our deep learning neural network. And here's the dimensions. We had 10, 30, and 10. And this one does a very good job as well. Again, just some of them at the intersection that it doesn't quite get. Alright, so here's unsupervised learning. I just want to show you this because what it does is it's going to go through and basically try to determine the labels for us. We're not giving the outcomes. So when we do a fit, right here, you're seeing that we don't feed in YA or the outcomes. We're only feeding in the inputs or the features, the things that we're using to predict. And then you have the prediction here, the YP equals KM dot predict XB, and you can see that is also not using any of the Y values, obviously, but then we're going to compare it. Sometimes you have to reverse the true false, because it's going to maybe say I have 2 groups, and so this arbitrary labels are going to be assigned with unsupervised clustering, and sometimes you just have to correct that. You have to swap them. So YP equals 1 minus YP, just swap true false. Okay, so you can see that the unsegregated ones, it really has no idea how to classify these. You just have a bunch of points, and it's going to draw a line somewhere and say, okay, I'm going to separate it between these 2. And so that's for all of these. You really get poor performance on the top 3. And that's to be expected with unsupervised learning methods. You're not feeding it any of the correct true-false labels. Okay, but these, it should work a little bit better than it did. You can see that some of the advantages and disadvantages, common and simplest clustering algorithm, but you got to specify the number of clusters. So here I had 2 clusters. I thought it would do better than that, but you got to specify, hey, here's how many different sets I have, and then it's going to try to group them based on the methods of the k-means. Okay, so basically if increase the distance between 2 sets. Okay, you have the Gaussian mixture model. One of the nice things about this is that you do get a measure of uncertainty in the solution, where it's going to show you not just a true false, but number in between. So you might have to just round it off to 0 or 1 or true false for the final solution if you need that. But sometimes that uncertainty is desirable. So if it says it's 60% sure that it's true, 40% sure that it's false, then you can take that into consideration. Okay, here is the Gaussian mixture model. You can see the top three, as expected, they don't perform very well, but the bottom three, you do have some success there. And then you have spectral clustering as well. This is segmentation-based object categorization, and you can find clusters when the data doesn't meet the requirements of some of the other algorithms. This is a good one to try if the other ones aren't working. All right, there can be slow convergence, so there are some problems with this one. And as expected, the top ones don't work well, but as we had poor performance from the other two on these, you can see that spectral clustering did very well on both of these. We didn't give it the labels of true false, and it was able to pick those out itself. All right, so you can do classification through supervised or unsupervised, or you can even do semi-supervised as well. So some of the labels are there. And there's a source code here. There's an exercise later. I'll go over this one later, where we're going to use a temperature control lab and try to classify when it is on or off. And so you have an exercise here where we're going to test all of the classification methods on this data set.